around outside. Okay, now museums are really important places, and I think especially today with our concerns about climate change, environmental destruction, museums are repositories for the organisms that inhabit our Earth, and we learn a lot about their distribution, their abundance, things like that. And it's the only place where this historical data is kept and can be referred to by contemporary workers. So they're certainly very important institutions, but they're also neat places because they record historical ideas, and science is about learning, changing your mind, reevaluating your hypotheses, and this is one example of I guess the tree of life, an early tree of life that is on display in the collections room. I took this photo this morning because I thought it was so interesting. Wonderful drawings of the plethora of animals, but it's quite outdated, and there's also things on it which are perhaps somewhat offensive. You wouldn't perhaps get away with today, putting in evolutionary order different races around the world. But at the time when this was produced, that was the thinking. So I'll move on quickly from that. But I thought it was interesting to just think about what museums mean in terms of the present world that we live in and what scientific information it can give us, but also the historical aspect. Okay, so other than a curatorial job at Yale, I also am pursuing several scientific projects. And one of them is sort of a carryover from my dissertation at UC, and that's thinking about how organisms respond to global environmental change. And my interval of focus is the Cenozoic again, the last 65 million years. And I'll give you two examples of how the environment has changed around the world. Firstly, with continental drift, reconfigurement of continents around the world. That has greatly changed oceanic environments. Continents have moved apart, some have also moved closer together, and this has greatly affected how organisms are distributed around the world, and also how the oceans behave. In particular, what we call oceanic gateways have sometimes opened and also closed, and I'll show you a specific example of that in a second. We also know that climate has changed considerably in geological times. So the curve on the right shows you an oxygen isotope curve and a rough temperature curve that's based on the isotopes through the Cenozoic. And cold is towards the left-hand side of that graph, warm is towards the right, and you can see that back in the Paleocene and Eocene, the world was a lot warmer in general than it is today. And since the early Eocene, it's gone towards colder temperatures. There's been a trend towards colder temperatures, including some quite dramatic changes. For example, at the Eocene-Oligocene boundary, about 35 million years ago, there's a very dramatic cooling event. Global temperatures are estimated to have dropped around 7 degrees in pretty short order. And that's possibly related to major changes in continental configuration. The opening of new oceanic gateways, passages for water to flow through, and that affects the climate. We also see there was a warming during the early and middle Miocene, and that's quite significant. But then quite sharp cooling towards the present day. And of course, we're potentially changing that trend with our recent historical modification of the climate. Okay, now a good example of how continental drift and plate tectonics has affected oceans is the Panamanian Isthmus, which has risen up out of the sea over the last 20 million years or so, forming a continuous land bridge probably about 2 million years ago. It's been a slow process, and at one point, maybe 5 to 10 million years ago, there was a nice archipelago chain of islands through that region that was gradually restricting movement of water between the Atlantic and the Pacific Ocean. Of course, now that's completely blocked off, and that has had tremendous effect, obviously, on distribution of organisms between the Atlantic and the Gulf of Mexico and the Pacific. And fortunately, for paleontologists, there's a wonderful rock record in the Panamanian area. It's always good when you've got rocks that are being rapidly uplifted because you can record marine environments and have a lot of exposure. And that is the case right here, a lot of uplift. And we can have a look at rocks of Miocene all the way through the Pleistocene age. It's really a wonderful natural laboratory to go and study. That's why the Smithsonian, well, in part, has a tropical research institute down in Panama, along the Panamanian Canal. And I think Dave has spent quite a bit of time there over the years, studying the echinoderms, I guess. Okay, and just getting people thinking about oceanic circulation. This is how it looks at the present day. And that would be what's known as the Drake Passage between Antarctica and South America. And that opened around 40 million years ago. And that's coincident with that rapid cooling at the beginning of the Oligocene, the 7-degree drop in temperatures. At that time, this current that runs around the bottom of Antarctica got going. It's called the Circum-Antarctic Current. That isolated the Antarctic continent, and that's when it became ice covered permanently for the first time. Prior to that, it was quite nice balmy temperatures down in the Antarctic, and also I should say back in the Eocene and Oligocene, it was quite nice up in the Arctic. That's not the case today. We have a very strong gradient of temperatures between the equator and polar areas. Okay, and this is an example of this temperature gradient, just to show you how strong it is. Now this has a tremendous effect on the distribution of organisms, and one of the things I'm particularly interested in is known as provinciality. Province is a geographic area which has a fairly distinct fauna, distinct assemblage of organisms. And I'll show you an example here of a snail which is restricted to it's known as the Indo-Pacific. This is during the Miocene, a scallop that's restricted to the Northwest Pacific, and a few other organisms that have quite limited distributions. And one of the projects I've been working on is quantitatively showing how that's changed through time steps from the Eocene all the way to the Pleistocene. And I show in these graphs, you don't have to concentrate too much on the details, but different colored blobs represent different provinces. And as we jump through to the Pleistocene, you can see many, many more blobs, and also many that are distributed along these north-south coastlines. And that's significant, because what we've done since the Eocene is strengthened this thermal gradient. We've gone from very warm waters in the equator to the cold waters of the Arctic, and that restricts organisms from migrating north and south along these coastlines. So therefore you get you get boundaries that prevent migration north and south, and distinct assemblages of organisms along those coastlines. So there's many, many more marine provinces at the present time than there were